For more than half a century, humanity has stared at Mars and seen destiny, a frozen desert world hanging silently in the night sky, a planet that scientists describe as our backup civilization, a place where future cities may rise beneath transparent domes while human beings walk across red valleys under an alien sunset. Entire generations have been raised on this vision. We are told Mars is the next step, the next frontier, the next giant leap. But buried underneath the optimism in interplanetary exploration is a question so disturbing that most discussions avoid confronting it directly. Not, how do we get to Mars, but something far more terrifying, how do we leave? Because traveling to Mars is only half the problem. The real nightmare begins after landing. Monitoring, once human beings touch the Martian surface, they are trapped inside one of the most hostile mechanical environments ever encountered by a machine built on Earth. And every second they remain there, physics begins dismantling the only vehicle capable of bringing them home. This is the part of Mars colonization that rarely appears in cinematic animations or glossy presentations. The return trip, and the assumption that after sitting abandoned on Mars for over a year, exposed to radiation, dust infiltration, chemical corrosion, cryogenic instability, violent thermal cycling, and relentless entropy, a rocket will somehow ignite flawlessly on command and carry astronauts back into orbit. That assumption may be one of the most dangerous engineering gambles in human history, because according to many physicists and aerospace engineers, the hardest part of Mars is not landing, it is surviving long enough to escape. And when you examine the actual physics involved, returning from Mars begins to look less like a mission and more like a miracle. Martian everstops, despi FT, imagine parking a Formula One car at the bottom of the ocean for 2 years, then suddenly asking it to win a race at maximum speed. No repairs, no technicians, no replacement parts, only pressure, corrosion, salt, temperature changes, and time slowly eating away at every component. Now replace ocean water with Martian dust. Replace salt corrosion with perchlorate oxidation. Replace humidity with ultra-dry electrostatic abrasion. And replace the Formula One engine with a rocket powerful enough to launch human beings off an alien planet. That is the true engineering reality of a Mars ascent vehicle. The public often imagines rockets as machines that either work or fail instantly, but in reality, spacecraft die slowly. Tiny seals weaken, lubricants degrade, microscopic fractures spread through metals. Electrical systems become brittle under radiation. Thermal expansion slowly warps precision-engineered components, and Mars accelerates every one of these failures. The planet appears calm from orbit, but on the surface it is an environment of relentless mechanical violence. Temperatures can swing by more than 100 degrees Celsius within a single Martian day. Metal contracts violently at night, then expands again after sunrise. This process repeats hundreds of times during a surface mission. Every expansion creates stress. Every contraction creates fatigue. Every cycle weakens the structure a little more. On Earth, maintenance crews constantly inspect aircraft engines for this exact reason. On Mars, there are no crews, no hangars, no repair infrastructure. No industrial supply chain, only astronauts depending entirely on a machine that has been quietly decaying for over a year. And unlike ordinary machinery, rockets operate at the edge of physical tolerance. A tiny crack inside a combustion chamber is not a minor problem. It is an explosion waiting for ignition. THE rocket AQAION, T musmir celeste far malo INS PFLHT. At the center of this entire problem lies one equation. An equation so fundamental that it governs every rocket ever built. The Tsiolkovsky rocket equation. This deceptively simple relationship determines whether a spacecraft can escape gravity or die trying, and the equation is brutal. Turing, because rockets suffer from a horrifying mathematical curse, the more fuel you add, the heavier the rocket becomes. But heavier rockets require even more fuel to lift that extra fuel, which requires even more fuel. And the cycle spirals exponentially. This is why rockets are mostly propellant. The actual astronauts' equipment, habitats, food, computers, and life support systems represent only a tiny fraction of the total launch mass. Mars makes this problem far worse. Its gravity is weaker than Earth's, but still powerful enough to demand enormous thrust during ascent, and unlike Earth, Mars provides almost no atmospheric assistance. Its atmosphere is less than 1% as dense as ours. That means a returning spacecraft cannot rely on aerodynamic lift or efficient atmospheric maneuvering. It must brute force itself into orbit almost entirely through raw rocket power. To survive this ascent, Turing engineers must protect the return vehicle from the Martian environment for over a year. But every layer of protection adds mass. Radiation shielding adds mass. Thermal insulation adds mass. Dust resistance systems add mass. Redundant electronics add mass. Backup valves add mass. Protective housings add mass. And the rocket equation punishes every kilogram. Not linearly. Exponentially. Eventually, the mission reaches a terrifying point where protecting the return rocket sufficiently makes the rocket too heavy to deliver to Mars in the first place. This is the hidden trap of Mars exploration. The more you prepare for survival, the harder survival becomes. TCLFS to escape even if engineers solve the structural problems. Another enemy remains thermodynamics. Modern high-performance rockets rely on cryogenic propellants like liquid oxygen, liquid methane, liquid hydrogen. These fuels are stored at temperatures so cold they exist only barely above absolute zero. Liquid oxygen must remain around minus 183 degrees Celsius, liquid methane around minus 161 degrees Celsius. These are not engineering preferences, they are physical requirements. If the propellant warms even slightly, it begins transforming into gas, and gas expands, which means the fuel slowly escapes. This process is called boil-off, and on Mars, boil-off becomes catastrophic. Because astronauts cannot leave immediately after landing, Earth and Mars orbit the Sun at different speeds. The launch windows for efficient return missions open only every 26 months. Meaning astronauts may wait more than 500 days before they can even attempt to leave. For those 500 days, heat constantly leaks into the fuel tanks. No insulation is perfect. No thermal barrier is absolute. The second law of thermodynamics guarantees that heat always moves toward colder systems, which means the Martian environment is continuously trying to destroy the rocket fuel needed for escape. Day after day, month after month, the spacecraft slowly loses the very propellant required to survive. By the time the departure window opens, the rocket may no longer possess enough fuel to reach orbit. Right? The escape vehicle literally evaporates while sitting on the surface. T-Martian, D-U-S-T-P-R, B-U-N-S-A-L-V-A-B-L-I, but perhaps the most frightening threat is not fuel. It is dust. Martian dust is unlike ordinary Earth sand. On Earth, wind and water gradually smooth particles over millions of years. Mars has almost no liquid water. Its dust remains sharp, jagged, and razor, like at microscopic scales. Worse still, the dust contains toxic perchlorates, highly reactive chemical compounds capable of corroding metals and damaging organic material. But the true nightmare comes from electrostatics. Because Mars has a thin atmosphere and constant exposure to solar radiation, the dust becomes electrically charged. It clings to everything. Spacesuits, solar panels, mechanical joints, optical sensors, engine seals. Apollo astronauts experienced similar problems with lunar dust, calling it one of the worst engineering hazards of the moon missions. And Mars is even more dangerous. The dust infiltrates microscopic gaps inside machinery. It contaminates lubricants, scratches surfaces, blocks injector nozzles, damages seals. Over time, the rocket begins dying from the inside. And here is the terrifying part the astronauts may never know. The clogged injector might remain undetected until ignition. The weakened seal might survive every inspection right until full engine pressure arrives. The damaged valve may appear functional until the exact moment the launch sequence begins. Rocket failures do not happen gently. They happen violently. Combustion instability, structural rupture, explosion. A Mars ascent failure would occur hundreds of millions of kilometers from Earth with absolutely no rescue possible. No backup launch pad, no emergency evacuation, no second vehicle waiting nearby. Only silence. And even if the machinery somehow survives, the human body faces another impossible burden. Radiation. Mars lacks a strong global magnetic field. Earth's magnetosphere shields us from enormous amounts of cosmic radiation and solar particles every single day. Mars has almost no such protection, which means astronauts on the surface endure continuous exposure to high energy radiation capable of damaging DNA, increasing cancer risk, degrading the nervous system, and possibly impairing cognition itself. A solar storm during the mission could become lethal within hours. To protect astronauts adequately would require heavy shielding, but heavy shielding means more mass. And once again, the rocket equation returns like a mathematical predator. Every solution creates another problem. Every layer of protection makes escape harder. Until Ruffo and Durrell, I told off to I saw Tom, perhaps the deepest psychological shock of Mars is this: if something breaks, nobody is coming. On Earth, engineers solve problems through infrastructure. Factories manufacture replacements. Technicians repair systems. Supply chains deliver components. Emergency crews respond instantly. Mars has none of these things. A crew on Mars exists inside complete industrial isolation. Every tool, every circuit, every spare component, every survival system, all of it must work. Because if a single critical system fails beyond repair, the crew does not experience inconvenience. They become a permanent human presence on another planet, dead or alive. And this changes the entire philosophy of exploration. Mars is not Antarctica. It is not the moon. It is not a remote research station. Turing, it is a planetary trap separated from Earth by hundreds of millions of kilometers of vacuum. There is another assumption quietly embedded inside nearly every public discussion about Mars exploration. An assumption so ordinary that most people never stop to question it. The assumption that machines can remain operational without civilization around them. On Earth, no complex machine truly survives alone. Commercial aircraft are constantly inspected between flights. Nuclear reactors require permanent oversight. Submarines undergo continuous maintenance. Even modern automobiles rely on global manufacturing systems capable of placing degraded components almost instantly. Complex technology is not independent. It survives because civilization surrounds it like an immune system. Every sophisticated machine on Earth exists inside an invisible web of technicians, factories, software updates, replacement infrastructure, industrial logistics, diagnostics, and repair chains. Mars removes all of that. A Mars mission is not merely transporting astronauts across space. It is attempting to compress an entire technological civilization into a handful of spacecraft components and hoping that civilization remains functional after years of exposure to an alien world. Turing, this changes the meaning of mechanical reliability completely, because reliability on Earth is often an illusion created by maintenance. A machine appears reliable only because human beings continuously prevent it from failing, but on Mars, entropy accumulates uninterrupted, and entropy always wins eventually. The danger is not usually dramatic, catastrophic destruction. The danger is gradual deviation, tiny microscopic changes, a seal becoming 0.2 millimeters less elastic, a fuel line developing microscopic crystal formation, an electrical connector slowly corroding under radiation exposure, a thermal shield losing a fraction of its insulating efficiency. None of these failures appear dangerous individually, but complex systems do not fail because one thing breaks. They fail because many tiny degradations synchronize at the worst possible moment. This is what engineers call cascading failure, and rockets are among the most cascade-sensitive machines humanity has ever created. A tiny sensor error can alter fuel flow. Altered fuel flow changes combustion pressure. Changed combustion pressure creates vibration instability. Vibration instability fractures engine components. And within seconds, the entire vehicle is destroyed. On Earth, thousands of engineers analyze rocket systems continuously before launch. Mars crews will not have thousands of engineers. They will have a few astronauts isolated on another planet attempting to diagnose problems with limited tools, limited spare parts, delayed communication, and constant psychological stress, because even communication with Earth suffers from the laws of physics. At maximum distance, radio signals between Earth and Mars can take over 20 minutes one way, which means astronauts cannot rely on real-time assistance. Every emergency becomes psychologically terrifying. Imagine discovering a fuel pressure anomaly before launch. On Earth, a mission control responds instantly. On Mars, every question enters silence for nearly half an hour before a response even begins returning. In a crisis, that delay feels eternal. And this isolation creates something even more dangerous than mechanical uncertainty. It creates cognitive pressure, fatigue, stress, fear, decision paralysis. Human beings are not perfectly rational systems under prolonged existential pressure. Even highly trained astronauts experience cognitive degradation under isolation and confinement. Studies from Antarctic stations, submarine deployments, and long-duration space simulations repeatedly show increases in depression, sleep disruption, emotional instability, and impaired decision-making over time. Mars missions multiply all of these conditions simultaneously: extreme confinement, extreme danger, extreme distance, extreme isolation. And unlike low Earth orbit missions, Mars crews would live with a terrifying psychological truth permanently sitting in the back of their minds. If the ascent vehicle fails, there is no rescue mission. Not because humanity lacks compassion, but because orbital mechanics do not permit immediate rescue. Earth and Mars are often separated by hundreds of millions of kilometers. A rescue mission could take many months or even years to arrive, which means astronauts on Mars may become the first human beings forced to psychologically adapt to irreversible abandonment by physics itself. That changes people, and it changes mission outcomes. Beauty among ISAs compared to Mars. The public often compares Mars missions to the Apollo program. But this comparison hides the true scale of the problem. The moon is close. Astronomically speaking, it is practically touching Earth. Apollo astronauts could return home in days. Turing mission control maintained near real-time communication. Emergency abort trajectories existed during much of the mission. Supplies could theoretically be launched relatively quickly. Mars offers none of these advantages. Mars is not a nearby expedition. It's interplanetary exile, and distance changes engineering in brutal ways. Every kilogram becomes precious. Every system must survive longer. Every mistake becomes permanent. Even basic medical emergencies become existential threats. A burst appendix on Earth is dangerous. A burst appendix on Mars may be unsurvivable. A dental infection, a fractured bone, a blood clot. Any of these can evolve into mission-ending disasters when definitive medical infrastructure is millions of kilometers away. This forces Mars missions into impossible redundancy requirements. Backup medical systems, backup environmental systems, backup communication systems, backup power systems. But redundancy means mass, and once again the rocket equation returns, always the rocket equation. Like gravity itself, it waits beneath every engineering decision, punishing complexity, punishing protection, punishing survival. TNRG problemas, mortarafbiamos piopa modern civilization exists because energy is abundant. Mars is an energy-poor environment. Solar power sounds attractive until dust storms begin. Some Martian dust storms grow so large they engulf the entire planet, not for hours, for weeks, sometimes months. During these storms, sunlight reaching the surface drops dramatically. Solar panels become coated in electrostatic dust. Power generation falls. Heating systems weaken. Life support systems become stressed. Battery reserves drain. And all the while, temperatures continue collapsing during the Martian night. NASA's Opportunity rover survived far beyond its expected lifespan, but eventually died during a dust storm because insufficient sunlight reached its solar panels. Now imagine that same scenario involving human beings depending on electrical systems to breathe. Nuclear reactors appear to solve this problem. But nuclear systems introduce another terrifying category of engineering risk: heat management, radiation shielding, mechanical cooling reliability, launch safety concerns, long-term reactor degradation. Again, every solution creates additional layers of complexity, and complexity itself becomes the enemy because complex systems fail in complex ways. Even if the spacecraft, even if the fuel survives, even if the engines ignited, the human body itself may become the limiting factor. Mars gravity is only 38% of Earth's gravity. That sounds manageable at first, but biology evolved under Earth gravity for hundreds of millions of years. We do not fully understand what partial gravity does to human physiology over long durations. Astronauts in microgravity already suffer muscle atrophy, bone density loss, fluid redistribution, during immune system disruption and vision changes. Mars gravity may reduce some of these effects, but perhaps not enough. No human being has ever lived in partial gravity for years. No one knows whether children could develop normally there. No one knows whether cardiovascular systems can permanently adapt. No one knows how the brain responds psychologically to permanent confinement beneath artificial habitats on a dead world where stepping outside without protection means instant death. Mars colonization discussions often treat humans like adaptable software, but humans are biological organisms shaped by Earth. Earth's atmosphere, Earth's gravity, Earth's magnetic protection, Earth's ecosystems. Mars strips all of these away simultaneously, and evolution does not quickly forgive environmental mismatch. About Mars, perhaps humanity will eventually solve these problems. Perhaps future material science will create self-repairing machinery. Perhaps autonomous robotics will maintain spacecraft continuously. Perhaps advanced nuclear propulsion will reduce travel times dramatically. Perhaps artificial intelligence systems will manage infrastructure more effectively than human crews. But none of those systems exist today at the level required for reliable Mars return missions. And that distinction matters enormously because public imagination often confuses aspiration with capability. Wanting something intensely does not make physics easier. History is filled with civilizations that believed ambition alone could overcome natural law. Nature eventually corrected every one of them. Mars may become the ultimate correction. Because Mars does not merely challenge humanity technologically. It challenges the deeper assumption that intelligence automatically grants dominion over hostile environments. The universe is under no obligation to accommodate human survival, and Mars may be the first place where civilization truly confronts that reality without the protective buffer of Earth. For the first time in history, humans may enter an environment where one failed seal, one cracked valve, one corrupted sensor, one microscopic engineering imperfection separates life from extinction. Not metaphorically, literally, and that is why returning from Mars is not simply an engineering problem. It is a confrontation between human ambition and the deepest physical laws governing matter, energy, entropy, and survival itself. The terrifying possibility is not that Mars is impossible to reach. The terrifying possibility is that humanity may reach Mars before it fully understands how to survive there. And history shows that exploration becomes deadly whenever excitement outruns understanding. Human civilization love stories about courage overcoming obstacles. But physics is not inspired by courage. The laws of thermodynamics do not negotiate. Entropy does not admire ambition. Radiation does not care about dreams. The universe operates through physical law with absolute indifference. And Mars exposes that indifference with terrifying clarity. To return safely from Mars, humanity must solve multiple unsolved engineering problems simultaneously: long-term cryogenic fuel storage, dust-proof precision machinery, radiation shielding, autonomous maintenance systems, ultra-reliable launch architectures, self-sustaining surface infrastructure. And every one of these systems must function perfectly after years in one of the harshest environments known to science. Not mostly functional, perfectly functional. Because in rocket propulsion, during a 1% failure can still kill everyone. The frightening truth is that humanity may already possess the technology to land on Mars, but landing was never the hardest part. Coming home is. And until civilization learns how to defeat entropy on another planet, Mars may remain exactly what it has always been. Not humanity's second home, but a one-way journey into the unforgiving machinery of the universe.